Here we'll talk about filling the gap between rover camera and orbital views using super-resolution restoration. Watch this.
Thank you very much, Gerhard. So I'd like to talk about a method that was developed that was never in the original project plan. It was something that was developed as serendipitous technology, but it has had quite a big impact on our ability to work with fusing orbital and rover data. So I'm talking about a visual gap, which is if we're trying to fuse rover camera data with orbital data, what we find is that because of the very narrow baseline between the two cameras on board the rover, which I believe is up to 50 centimeters currently, and will be 60 centimeters with XMR's Chemcam, something of that nature. 50, that's right, and it's 35 for its smaller distance for the MER at least. And that because of that very limited baseline, the actual stereo range that you can go out to and still produce three-dimensional results is only on the order of 5 meters. So you can't make 3D measurements beyond that, other than actually moving the rover to a different position. So the difficulty is that the orbital data, although it's taken with an equivalent of a spy satellite camera like Worldview that we have around, which is now in the civilian domain, if you've got deep enough pockets to pay the 10,000 euros per scene, then basically you can then view scenes as if you're from 20 meters away. So we've got this visual gap between 5 and 20 meters, which means that we cannot provide an illusion as if we are on the surface of Mars, which is obviously one of the things we're trying to do with the project. So 25 centimeter high-rise images allow you to see the details of surface from the orbit, but when using such imagery for simulation of a rover camera viewpoint, such images can only really create realistic views for this 20 meter and beyond range. So that means there's this big resolution gap between the high-rise orthorectified images and the rover images. However, because of the fact that NASA has been very keen to re-image the actual area that rover is moving to and through in order to look for hazards ahead, and that wasn't originally part of the plan, because when MER exploration rovers were landed on the surface of Mars, there was no high-rise camera. There was nothing like that. In fact, it took 5 years until there was such imagery. And so what we've tried to do here is we've taken some pre-existing work that was developed for close-range imagery, and we've tried to model and modify these algorithms so that they will operate and correct for atmospheric distortions, as well as, and not for dust, because we can't do anything about that, but certainly the optical system of the camera, as well as the resampling that's actually done with time delay integration on board the high-rise instrument. So each view is subject to different atmospheric blurring and scattering, and the key is that we have to have sufficiently high atmospheric transparency, sufficiently low aerosol optical depth in order to be able to apply this technique. And of course, the great thing would be if we have an automatic way of determining the clarity of the image, if only. We're still working on it. It's not an easy problem. It's a problem that is quite prevalent with Earth observation data for trying to get rid of atmospheric scattering, but it's not a problem that can be straightforwardly solved. So we're taking the multiple images that we have over the 3 rover traverses, and we're looking at trying to exploit the fact that we have each image taken at quite different angles. So we have large variations in zenith view angles, with not very much variations in solar angles, because of the fact that it's locked in the Mars Reconnaissance Orbiter, is locked into a sun-synchronous orbit with an overpass time of 3 p.m. local time. So we don't have a vast range, and because all of these rovers are very close to the equator. The sun doesn't move very much in the sky. So the technique that has been developed is optimal for orbital imagery. We use subpixel information by applying a subpixel area-based least squares correlation algorithm for looking for slight translational shifts in a stack of lower resolution imagery. I'll show a little more about the algorithm in a moment. And we restore the pixels onto an orthorectified grid. This is absolutely critical. We have to have, and we do of course because we have multiple angles as part of the repeat imagery, we have to have a 3D model plus an orthorectified image at 25 centimeters as our starting point. In this particular case, the super resolution is not restricted to the theoretical factor which is listed in a rather old paper by my colleague Andrew Zisserman from Oxford Computing Department, where he demonstrated that you could only have a maximum resolution enhancement on the order of 1.75 if you only have single pixel jitter in the actual individual images. And we've initially applied it, as I say, to a stack, and we were very surprised with the first sets of imagery for an area called home plate for MER-A, but we then applied it to much larger areas. And I want to demonstrate and prove to you today, I hope, that we really are getting an enhancement factor of the order of 2 to 5, i.e. much greater than this theoretical limit which had been placed before. So the GPT algorithm is shown in outline form. It's just been accepted for publication in Planetary Space Science. Bit of a struggle to get them to find the reviewer and get them then to take our revised version. But anyway, it's all happening now. So it starts off with multiple aligned low resolution images and a reference orthorectified images, as I've already said. Here we have the input low resolution image and the reference ORI. We generate a subpixel tile motion set of vectors using adaptive least squares correlation region graying algorithm that we developed in 1987 called Gotcha, which is now in its 5th rewrite. It's now back in C++, having been through Java and IDL in between time. And this is used to resolve the actual distortion using partial differential equation total variation. I refer you to the paper for greater details within segmented tiles that we segment. So we apply Gotcha to this stack of low resolution images to prepare a subpixel translation map. We then perform an image segmentation on this subpixel translation map, which we then run through this PDE total variation in order to retrieve the results onto a final output, which is at 5 times or 8 times or whatever it might be the original resolution in order to get the output super resolution restoration. So as with all of these things, the proof of the pudding, as we say in English, is in the eating. If we start here, and you'll notice what I've written here is the date and the high-rise image number. And what you'll see is that for they're quite different dates, different years. These are each of the images. And then taking all of these images together, using that schema I just showed, we get a super resolution result at 5 centimeters. So 5 times the original nominal resolution. So to show you, these are very early results, which still contain fixed pattern noise. In a moment, I'll show you that the latest results certainly don't have anything like this speckly noise. But here you can see individual rock features. Here you can see an edge, and you can see much more detail in the actual edge itself, with the individual rocks displayed. And finally, another set of rocks, you can see the original blurred version in the orthorectified image, and on the right-hand side, the super resolution version. And finally, what I think is the most convincing is on the left is an orthorectified image, on the right is the super res result, and you can see quite clearly that you have these features, which are quite obviously the tracks of the rover that have taken place during that time period. So, starting with that, we've then each one of these 2,000 samples by 1,000 lines takes 3 days of computing on a 16 core. And that isn't because it's inefficient, that's just because of the fact that it's doing a massive amount of I/O and a massive amount of computation. So at the moment, if you count up the number here, it took about around a month to actually compute these super res tiles for the entire extent of the MER-A rover. Here's an example of one of those tiles, and here you can see the individual resolution enhancement in this particular case without any of the artifacts which were shown in the previous image. Here's an example where we only had 5 images, and 2 of those were still reasonably dusty and therefore were rather difficult to actually use to get higher resolution. Here's an example which you've already seen of the 2 displays. Here's an example now we have of MSL, where we have the entire track, and now we've done some clever stuff on a few blades so we can actually process it a bit faster than we could before. And that shows you the corresponding high-rise resolution, and this is the corresponding CTX resolution. So for the entire traverses of all 3 rovers. This is an example of the Shaler formation that Sanjeev may or may not talk about in a moment. And here you can see the super res on the right, and on the left-hand side, the original high-rise image. This is another area unidentified, and again, you can see the increase in resolution that you have as a result. In this particular case, 6¼ centimeters. So we've also applied the same thing to Chemcam images, courtesy of the Chemcam PI, Roger Weens, at Los Alamos. And we took a stack of these Chemcam images and were able to, again, do super res, but this time only about 1/2 times, or 1¾ times. But of course, we can now see the individual grains, which is what the scientists wanted to see. Whereas you couldn't see them in the original image. So here you can see all of the original granularity that they were interested in. Done the same thing as well, because on MER, it was demonstrated by Jim Bell in a paper many years ago, that you could use the fact that every single time you took another image from the rover camera, you got a jitter of 1 pixel in either direction. And so we've applied the same thing to the MSL Navcam data, and here you can see the result of the super res that's been applied to the Navcam. And obviously we can do this with PanCam, and we have lots of plans and ideas for how to do this with the HRC in particular, but also for the WAC, so we can actually get much higher resolution, at least by a factor of 1.75. So, you probably don't believe me. You think I'm selling you, boot whiskey or whatever it's called. Unfortunately, we can't send anyone to Mars to actually check our results. But we can use image processing to check out on whether or not we can observe more fine-scale detail. Because we did send rovers with geometrically calibrated cameras, so we can compare what we see on the ground with what we have generated from spaceborne orbital views. And I hope to demonstrate the best proof that we can for now. If any of you have got any smart ideas of how we can do it better, I'm really interested to hear, because of the fact that we have thought and racked our brains how to prove that we are actually achieving this on Mars. Obviously, we're doing tests on the Earth with Pleiades images, but that's a longer term project. It's a lot more work as well. And we're also working with the UK Ordnance Survey to use ERA-bot imagery, because they're interested in getting very, very cheap super res data sets from ERA-bots in the future. So one way we can do it is with the data itself, using image processing techniques. And in this particular case, we can apply a relatively simple filter that Fred Califf from the MSL project at JPL applied. And this is looking at the local variance. And so we can estimate the surface roughness from the image texture. And on the left-hand side is the original high-rise image. On the right-hand side is the super-res image. And you can see there are a lot more fine-scale detail in the right-hand one, much clearer than you can see in the left. But that's only a qualitative way of looking at whether or not we're getting enhanced resolution. A more quantitative way is to actually take the Rover camera imagery, and in this particular case we take the vertically projected Navcam mosaic, which Bob showed how that was produced in the talk before me, and here on the left hand side we can take the super res restoration. Now they're not in exactly the same projection system, but we can measure the corresponding distance between the outer and the inner, and also between the outer and the outer part of the two wheels. We know what they are because that's published in the literature, so we can take the scale, and from that we can estimate that basically we can see that the standard deviation of the measurements is on the order of about 8 centimeters, so it's 1.6 pixels in the SRR, which is certainly within the bounds of the error, either from manual measurements or from edge detection, because we try both in these particular cases. So that one level demonstrates one level. Let's take it to the next stage, which is somebody says, well, what about rocks? So we've taken images. Here we have on the left the original high-rise image. The image on the right is the super res, and we have an automatic rock detector, which isn't brilliant. I can see all sorts of errors here, but it's on the order of 85% correct, as it is for most of such things. And we can see that we could see a lot more rocks in the super res than we can in the original image. In fact, if we put a grid over this and of 20 pixels size, which we have in the super res case at 1 meter, and in the other case at 5 meters, you can obviously see in any of these grids that we're picking up a lot more rocks. And here we can see that we're picking up something like 7 times more rocks from the super res than we are from the original. Now this obviously as well has a benefit, because it means that for future XMR's landing sites, so long as we can persuade Alfred McEwen to actually acquire lots and lots of repeat imagery, or we can do this potentially with CASIS but not to the same kind of resolution, we could apply super res and make sure, of course, that we're not going to land in a pit of snakes or rocks, as the case may be, and therefore ensure that it meets the engineering requirements, which is a much better way, I believe, than the thermal inertia methods that have been developed up until now. So we've performed finally a rock size distribution study along the MSL Rover traverse. We're looking at doing this as a science paper. We're looking at the rock size distribution, starting off with the Navcam imagery, with imagery which were half a centimeter, originally 5 millimeters, and then down sampled to 2.5 centimeters. We're taking the 25 centimeter high rise and the 6.25 SRR around the same areas, and we're comparing the two. There are obvious uncertainties like the misdetections, the Navcam projection distortions, miscounts around the border, particularly the Navcam vertically projected images, and there are also rock number variations because smaller rocks are sometimes mixed together and clustered as one rock in the lower resolution imagery. So I'm just going to show you 3 very quick examples. So here you see the rock, and you'll get the idea in a moment. Here we have the high-rise image at 25 centimeters, the super res at 6.25, and the vertically projected image for the same area. And here we have all the rocks which have been detected on those 3. And then we can compare the distribution. You can see the distribution is effectively flat in the case of the high-rise, increases up to about 50 centimeters in the case of the super res, and obviously you can see a lot more smaller rocks from the Navcam imagery because we're dealing with millimeter sized imagery. Another area here, you can see slightly different results, but we still get an increase in the actual detection of rocks from the super res in comparison to the high rise. And finally, the last area where we can see quite clearly we have this divergence at about 50 centimeters because of the fact that we have much higher resolution in the original Navcam. So in conclusion, the rock size distribution results that we have from the SRR, from the super res images and the high res image in Navcam suggest that the super res algorithm is able to bring out the individual rocks. Sizes less than 75 centimeter and larger than 30 centimeter, but it's not, which are not clear or unrecognizable in the original. We've got accumulated rock numbers between the super res and the Navcam, which show very good correlation. Therefore, we believe that the super res can much better support Martian surface studies as well as future path planning. You can see all of these, and we hope tomorrow to get the authorization to release that so that anyone can view all of these super res projects. And we've also demonstrated the capability to use repeat views for different kinds of cameras. Now, for the future, we plan, subject to UK Space Agency seeing the light of day, is that with the ExoMars Trace Gas Orbiter CASIS instrument, with support from Nick Thomas, the PI, we want to see if we can get as a standard product because of the fact they acquire all of these multiple angles as they're moving along tracks. So we can try and produce 1 meter imagery operationally along the track. And of course, we'll also have multiple overlapping color and we'll have stereo. So we can also produce much higher res DTMs as well as the high res images. But to do all of that, we need to do the final piece, which is we need to make this thing fast so that we could take a high rise scene and in 3 hours do a 100,000 by 50,000 picture, because at the moment it just takes ridiculously long time. Thank you.
Are there any questions?
When you're showing the rover track width, the super res had a systematically smaller measurement. Why would it be systematic?
Not noticed it, but let's have a look at it. Right. Right. Okay. So that's the track outer spacing in red, and in blue is the track outer spacing on the Navcam. And you're asking why is there this difference between the two, which in one case is on the order of 7 or 8 centimeters. The only way I can answer that is to say that perhaps the where precisely you put your pixel that you're using for determining the outer edge, that for some reason or other you're putting it into a different place. That's the only thing I can think of that could explain that.
Have you looked at more than one place? Is this just based on one track, or have you looked at more than one place?
Right. No, we haven't. And that's a perfectly valid thing for us to do. In particular, we should look at the tracks north of Victoria Crater because they're very clear indeed. And we should also look at some of the tracks near Shaler because there's some very good tracks there. Good point. Thank you.
You have to get super res images, you have to use a lot of computer power. You mentioned that you have rewritten your algorithm 5 times, but did you try somehow to cheapen, to make this algorithm more cheap? I mean, make some optimization that not to squeeze every single, but make it cheap enough to get the benefit of super res.
Yeah, we haven't tried that for super res, but we have tried it for something else. We confronted this problem with another NASA project, an instrument called MER-A, which stands for Multi-Angular Imaging Spectroradiometer. It's a 9-angle push beam instrument which flies on the EOS Terra morning platform, and we use a stripped down version of the Gotcha algorithm, which we call M3 for a whole variety of different reasons.
That's what everyone is using.
But it's only accurate to the nearest pixel. As soon as we put in subpixel acuity, which we have to have for the super res, then basically it just slows right down. That's the problem, is that subpixel acuity. Now with correlation, I realize you can fit things to correlation peaks in order to speed up the processing. We could change the matrix inversion that we use in the least squares. We have looked at various different ways of doing that, but nothing gives us faster, nothing gives us the speed up that we need at the moment, but we believe the GPU will.
Okay, one last question.
You said you were able to get rid of the speckled noise. Can you give an example of features where this happened?
You mean this this kind of fixed pattern noise? I think I showed you in the image on the MER track. If I go back, right. Yeah, this one doesn't have the noise in the same way. If you look at the Protus site and you look at particularly the latest MSL, there's no noise there, and it was just one term in the total variation that we modified to remove it. So we have got rid of it.
All right, thanks again, Peter.